Models of many processes can also be represented by continuous time systems. For example, if we develop our model using first principles method, that is by using conservation laws like mass balances, momentum balances, and energy balance, then we usually get our nonlinear continuous time models. Such models are called mechanistic models. For MPC, continuous time state space models are very much suitable and they are widely used. Continuous time state space models can be both linear and nonlinear in nature. The nonlinear state space model in continuous time can be written as follows. This is the state equation, and this is the measurement equation. In the state equation, f represents any nonlinear function that is dependent on x. The state, u, the control input, and time. For the measurement equation, g represents any nonlinear function which is dependent on x, u, and t. The state of the process can be more than one. Similarly, there can be more than one control inputs and more than one outputs of the process. In general, we can describe the size of the state, control input, and the output as follows. Here nx is the number of states, nu is the number of control inputs, and ny is the number of outputs of the process. The linear state space model can be represented as follows. Here, AC, BC, CC, and DC are the system matrices. The subscript C means continuous time. The first equation is the state equation, and this is the measurement equation. It is assumed that the students are familiar with the linear state space model from previous courses. Assuming that the number of states, inputs, and outputs are as defined here, we can define the sizes of these system matrices, and we can write it as follows. The state space model, both linear and nonlinear, will be used in this course. So we will have a much larger focus on this type of model structure. However, just to mention that MPC is also suitable for transfer function model. A transfer function model is represented as follows, where h of s is the transfer function, s is a Laplacian variable, and this model is in Laplacian domain, which is a frequency domain. The transfer function hs transforms the input us to the output ys. In this course, we will not be using transfer function models, so we will not talk about these kinds of models in detail. However, it is also possible to use transfer function model along with MPC. Now let us go back to our state space model. In general, a mechanistic model that is obtained by mass, momentum, and energy balances are nonlinear in nature. By now, we know a little bit about the different types of models. Now we will branch to the left, and then first, we will talk about the use of linear model to make linear MPC. Thus, if we have a mathematical model which is nonlinear, to make it useful for linear MPC, we first have to linearize the model. Of course, later in the course, we will also be talking about nonlinear models. But at first, let us have a focus on the left-hand side, which uses linear model of the process. Thus, in the next section of the video, we will talk about how do we linearize a nonlinear model to a linear model. For simplicity, let us at first rewrite the nonlinear model in continuous time. Let us now define the sizes of the states, inputs, and the outputs. Now let us assume that the number of states are nx, the number of inputs are nu, and the number of outputs are ny. For each state, there will be a nonlinear function. So for nx number of states, there will be nx number of nonlinear function or f. Let us write the f as a vector. f1 is the nonlinear function for the derivative of the first state. f2 is the nonlinear function for the derivative of the second state, and so on until the last state, nx. Similarly, for the measurement equation, g will also be a vector. Each g corresponds to each of the outputs, and each of them are nonlinear functions. Now, before we can linearize this nonlinear model, we first have to select an operating point. We then linearize the nonlinear model at the operating point, which is chosen by the user. The subscript op means operating point. We should understand that if this is a nonlinear function, and if we want to linearize it, we first choose an operating point and the linearized model will behave well around this operating point in the neighborhood of this operating point. However, if we go far away from this operating point, then the response shown by the linear model may not be the same as shown by the nonlinear model. So let us assume that the actual system dynamics are lying around this operating point. Delta xt, delta ut, and delta yt are small perturbations. Let us rearrange this one. So the delta are the deviation of the actual state from the operating point as shown here. Let us at first look at the state equation, just to remind you that for multiple states, this f is a vector consisting of more than one nonlinear functional values for each of the states. To linearize these state equations, we perform Taylor series expansion. Then we perform the Taylor series expansion around the operating point. Then we get the following expression. The Taylor series expansion of this expression, which is of course this expression, is that the first term is the functional value at the operating point. This term defines the partial derivative with respect to x, or the states, and the deviation of the state from the operating point. The third term is the deviation of the control inputs from the operating point and the partial derivative of the f evaluated for u. And similarly, we get higher order terms. To linearize the model, we neglect the higher order terms. Now let us substitute this xt. Xt is here. The functional value at the operating point is the same as the derivative at the operating point, so they cancel out each other. Also, one thing I would like to mention is that the partial derivatives of f with respect to x and also with respect to u has to be calculated at the operating point. So this vertical line means this partial derivative evaluated at these points. Then finally, we get the following expression. This term is the system matrix AC, and this term is the system matrix BC. First, we have the following, and this is the linearized version of the nonlinear model. Now let us also write the expression for AC and BC, and they are defined here. Since this f may be a vector because there are more than one number of states, thus we have to take the partial derivative for each of the f. In this example, we have nx number of f, so we have to take the partial derivative for each one of them with respect to each of the states as shown here. Thus, the size of the system matrix AC will be, thus AC is a square matrix. Similarly, in order to find BC, we have to take the partial derivative with respect to all of the functional values, but with respect to the control inputs. Let us write it here. Thus, the size of BC will be as follows. And we should remember that we should evaluate these matrices at the operating point. Thus, for the state equation, we will get a linear model, and the linear model will be in the deviation form, delta xt and delta ut, where this delta xt and delta ut means deviation from the operating point. Now let us also look for the output equation. The output equation is, and using the operating point, we know that. Let us substitute the value of yt from this expression here. Now, let us perform or take the Taylor series expansion of this nonlinear output equation. Then we will get, it is exactly the same way that we did it for the state equation. Here also we will neglect the higher order terms. These two terms are the same, so they cancel out each other, because if you put operating point here, then we get y operating point. So they are the same and they cancel out each other. This term has a special matrix, and similarly, this is also one of the system matrix. This is C of C and this is D of C. Then we get, this is the measurement equation, which is linear in nature. We can write the expression for CC using its definition, and since there can be more than one output, so G can be a vector. Thus, we have to take the partial derivative of each of the nonlinear output equations with respect to the states. The matrix has to be evaluated at the operating points. The size of CC is, and similarly, the expression for DC is obtained in the same manner. It is shown here. Thus, to sum it up, we have the linear equation as follows. Thus, the linear model is in the deviation form, and the deviation variables are delta xt, delta ut, and delta YT for states, inputs, and outputs. In the special case where the operating points are 0, we will have a simplified form of this linear equation. And in this case, the linear model is written as follows. This is the form which is very familiar to the students. Please remember that this form is only for the special case. So the general form is the deviation form, and we should always remember to subtract operating points when we want to calculate the deviation.